All right, here we go. AP Physics video 12.1. We're going to talk about rolling, things rolling. We did a little bit of this last year. We are definitely going to begin what we learned last year. All right, so here we go. So a smoothly rolling object. This is like a physics-y technical term, smoothly rolling. A smoothly rolling object is one which is rolling with no sliding occurring. All right. So there are a couple ways of thinking about an object that is, I'm going to just say rolling from this point forward, and unless I say otherwise, let's just assume that it is smoothly rolling, okay? So there's a couple different ways of thinking about a rolling object, because there are sort of two points of rotation about which you can think of the object, all right? So the most common one is this. The motion of a smoothly rolling object can be thought of a combination of both linear, like regular old translational motion, and angular motion. Okay? So what do I mean by that? Well, so when an object, let me see if I can get this to work. I don't think I'm going to, but so imagine you've got a wheel, right? Okay, and it's rolling along some surface, right? Draw the surface down here. Right? So the idea is, when that object rolls along the surface, there are two types of motion. So the first type of motion, the obvious motion, is since it's rolling, it's rotating, right? So you've got this rotational motion, right? So notice, as the object is rotating, what happens, if you just think about the rotation, what happens is the center of the tire doesn't move, right? The top point on the tire is moving forward, and the bottom point on the tire is moving backwards, right? So you get this motion where there's no motion here, there's forwards motion here, and there's backwards motion here. So that's the rotational motion. Okay? And so if you go back to the slide that I've got back here, our pure rotational motion looks like this, right? Your center doesn't move. The top point on the tire moves forward, the bottom point on the tire moves backward, okay? But it's not just spinning in place, right? It's spinning in place, and there's translational motion. In other words, the object is, these guys. Okay, so the other type of motion is this. As the tire is rotating, whoa, that's not what I wanted to happen. As the tire is rotating, it is also moving, right? Okay? And notice the important thing about it moving is that if you just look at the horizontal motion of the object, they're all the same, right? Like if you didn't consider the rotation, then the center of mass would be moving forward, the top of the tire would be moving forward, and the bottom of the tire would be moving forward, right? Because just everything is kind of moving forward together, right? Now, what's actually happening, though, is both of these two types of motion are happening together. And unfortunately, the smartboard won't let me both drag and rotate simultaneously. But so if you can imagine that occurring at the same time that this is occurring, that's when you get rolling, smooth rolling, okay? And so in red here, I've circled the pure rotation. So here's the pure translational motion. Okay, so smooth rolling is a combination of those two things. So at any given instant, the overall velocity relative to the ground, and that is important, the velocity of a point on the wheel relative to the ground is the vector sum of these. So the idea is when an object is rolling, the point at which there is contact with the ground, there's no motion. Okay, because the rolling motion wants the object to move backwards with some velocity, and the translational motion wants it to move forward with some velocity, and so it just stays at rest, okay? The center of the object moves forward at the velocity of the object, right? Because there's no motion due to the rotation, but there is motion due to the translational motion. And then the top point actually moves forward at a velocity that's twice the center of mass, okay? Here's another way of thinking about this. All right, this argument here, what it's actually doing is you're thinking about the wheel repeatedly tipping over, tipping over, tipping over. So it would look like this. Let's pretend that the wheel is a rectangle, okay? I almost tipped over. Oops. So the idea is, if my wheel rotates, okay, so here's my wheel right now, right? And so when it rotates, it's kind of tipping over. All right, shoot. Unfortunately, this won't let me, whenever it rotates, oh. Yeah. So if you imagine this thing tipping over, the idea is this point's not going to move, right? Because it's tipping over. This point's going to tip over slowly, and this point's going to tip over quickly, right? Because it's got a larger radius, right? Okay? And so the idea is our wheel is like this shape that is kind of just kind of repeatedly tipping over, right? So here's my pivot point. It's going to tip over. This point's going to go forwards. This point's going to go forwards faster because it's got twice the radius. Okay? So relative to the ground, at the point of contact, there's no motion. All right? The velocity of sort of the object is equal to the velocity of the center of mass. And then the velocity of a point at the top is double that. Okay? All right. So if you guys remind me, when I see you in class next, remind me, and I'll break out the wheel and we'll talk about this. There's a lot of stuff going on here, all right? So this will definitely help with a little bit of visual, okay? Okay, so let's see. So what else haven't we talked about here? All right. Now, so during smooth rolling, it is true that the velocity of the center of mass is just equal to the angular velocity of the tire times the radius, okay? So in other words, your jumper equations work. And if the wheel is accelerating, your jumper equations work for the acceleration too. Notice though, these are all specific to the velocity and the acceleration of the center of mass, because that is the only point on the rolling object that has the same velocity relative to the ground as the whole object, sort of, okay? All right, so how do we solve problems? All right, so I'm going to show you guys, oh, well, okay. All right, so let's see. So I guess before we get to problem solving, one other quick thing. So if you want to talk about the energy of a rolling object, the idea is when it's rolling, you're going to have both types of energy, right? You're going to have translational kinetic energy, regular old linear 1/2 mv squared kinetic energy, and you're also going to have rotational kinetic energy. So here I've used K for kinetic energy. T is translational, R is rotational. Here's our translational kinetic energy. Here's our rotational kinetic energy. All right, so it turns out if the object has a rotational inertia, which is I equals beta mr squared, okay, right? Because usually rotational inertia is some fraction times mr squared, right? So it turns out then what you can do is you can rewrite your rotational kinetic energy as follows. So we know that rotational kinetic energy is 1/2 I omega squared, right? So we're just going to substitute I in. So here's our I. And then if it's going through smooth rolling, then our angular velocity is just V over R. Okay? So notice here, what happens is the R's cancel, and you get this. You get 1/2 beta times mv squared. Oh, well, that's just beta times the regular old kinetic energy. Okay? So this is huge. If an object is rolling, what that means is, in old notation, our rotational kinetic energy will just be equal to beta times our regular old kinetic energy. If rolling. If smooth rolling. Okay, that will be true. It's got to be smooth rolling. Oops, I don't know what happened to my if. Oh no, I also don't know what happened to my smartboard. All right? So, if the object is rolling. Okay? All right, and so what that means then is if you want to find your sort of overall kinetic energy, add your translational and your rotational. So that's your translational plus your rotational. So that's this. So this right here represents the sort of overall kinetic energy of a rolling object. All right? So that is a useful tool. This is another one of those things that for whatever reason, I never see this in AP books, but I use it so much when I solve problems. This in particular, this in particular, I use a lot. And for whatever reason, I never see it in physics books, but Like, that's the jam in terms of solving problems where you've got an object that's rolling, okay? And it's super easy to prove. So if you use it, prove it, off you go. All right, so it turns out if the rolling object is accelerating, then there has to be a net force causing the translational acceleration and a net torque causing the angular acceleration, okay? So what I'm going to do here in a minute is I'm going to solve a problem which has an object rolling down an inclined plane, and I'm going to solve it using three approaches, okay? One of them is going to be using this energy idea here that we just talked about, all right? And the other two methods are going to sort of revolve around this idea that we've got net force causing translational acceleration and net torque causing angular acceleration, all right? So that's sort of where we're headed here in the notes, all right? So before we do, so here's the deal. So here's just a simple diagram of an object rolling, you know, maybe it's a sphere, a hoop, or whatever, it doesn't matter, okay, with a free body diagram, okay? So here's what our forces are. So gravity, remember, gravity acts at your center of mass. Gravity is going to pull the object down, all right? But what we're going to do is we're going to replace that force of gravity with the two components, okay? So our two components are Fg parallel, which is Fg sine theta, and Fg perpendicular, which is our Fg cosine theta, okay? Notice our Fg perpendicular goes through the point of contact. So that Fg perpendicular will not produce torque, okay? I should say that. I'm going to come back. I'm going to revisit that thought. Okay. And then similarly, our normal force is equal to our Fg perpendicular, so that goes that way. All right. Now, if this thing is rolling, there has to be friction. All right. If there was not friction, it would simply slide down the ramp. It wouldn't actually roll. All right. Remember, we said that if the object is rolling at the point of contact, there's no motion. And if there's no motion, that means there's no sliding, which means this must be a force of static friction occurring at the point of contact. Okay? Now, notice our Fg perpendicular and our normal force cancel, so that means our net force is simply going to be our Fg parallel plus our force of static friction, or minus, depending on how you set up your signs. But it's the contribution of those two forces. Okay? Now, here's the wild thing. We can think about this two ways. Option one is we can think of our pivot point as being the center of the tire, which makes some sense, right? Because it's rotating about the center. And if you do that, what happens then is gravity produces no torque. Our normal force goes right through our pivot point, and as a result, produces no torque. So if we consider the center point as our pivot point, then the torque is provided by friction. That's going to cause the tire to rotate this way, and that produces the rotation that makes the wheel go down the hill. All right, so that's one way of thinking about it. And it's actually, honestly, the most common way of thinking about it. But as you'll see as we go through the video, I don't think it's the easiest way to do it. There are times when it's easier to do that. And you'll sort of figure out, which method is best as you go through these. But I think that the other way of doing it is usually easier. So what is that other way? So the other way you can think about it is this. Remember, we talked about rotation being sort of this constant tipping over, right? So if we think of this as our pivot point, then what happens is gravity provides a torque that makes it tip over. All right, so our normal force is here, that provides no torque. Friction is right at your pivot point, that provides no torque. Fg perpendicular provides no torque, but your Fg parallel does provide a torque. All right, and that causes the wheel to sort of tip over and rotate forward. Okay, so to me, that's the best way of solving it most of the time. Okay? So what I'm going to do here is I'm going to show you three different approaches to solving an object rolling down a hill. Okay? I'm going to start with sort of the approach that we used last year, which is in terms of energy, which honestly, especially if you're dealing with acceleration, I think is the hardest way to do it. Okay? And then I'll work towards sort of the easier ways of doing it. Okay? All right, so here we go. So let's do this. So it says we can choose two methods, and it's actually three. As I wrote up my notes, I changed them a little bit, but I didn't change the slides to accommodate. So we're going to look at a couple different ways of finding the acceleration of an object rolling down a plane. All right? So the first way is in terms of energy. All right? Now, to be fair, the time at which I would use energy is not so much if you're interested in the acceleration of the object, but if you're interested in the height at a point or the velocity at a point. All right, in other words, if you've got a thing rolling down a ramp like this, and you know the height of the ramp, and you want to find the velocity at the bottom, right, that's a good indication that you're going to be using energy, right? Remember, we talked about that in class, that energy is a good tool if you know information about one point in an object's motion, and you're looking for information at another point in an object's motion, okay? So, that being said, we can use the idea of energy to find the acceleration. Okay, so I'm going to do that. It's not probably the most practical approach, but I'm going to be stubborn and do it anyway. All right, so here we go. Okay, so here's our inclined plane. Okay, whoops, that's not what I wanted to do. Here's our inclined plane. Here's our object. All right. Now, let's assume for simplicity that it starts at rest. It doesn't really matter, right? Because once we find the acceleration on an inclined plane is constant, right? Okay, so let's do this. So here's our inclined plane. It's got a height of h and a displacement of, let's call it delta x. Okay? And so what we're going to try to do is we're going to try to find the acceleration. But the way that we're going to do that is by figuring out some information about this bottom point, where the velocity is v, okay? So here are some things we know. So first of all, it's a rolling object. So let's suppose that our rotational inertia is just beta mr squared, you know, where m is the mass of the thing and r is the radius. Okay. Notice, so we're given the angle of our inclined plane. So here's our theta. Okay, so based on that, there's a relationship here between our height and our displacement. Specifically, the height of the ramp is just delta x times the sine of theta. Okay, and then I'm going to pull out one old kinematics equation. So one of the equations from the beginning of the year, and actually from honors physics, is this guy. So 2 times the acceleration of an object is equal to the displacement times vf squared minus vi squared. And for us, that's going to be this. 2 times the acceleration of the center of mass times the displacement is going to be v squared minus 0, where v is this velocity at the bottom. Okay? So that is that. So now let's see if we can figure out some stuff. So what I know is, I'm going to change colors. All right, so I know that the total energy at the top is going to equal the total energy at the bottom. Oh, you know, I should make a comment here. There's friction. So what about the work done by friction? So here's the deal with that. It turns out, remember, at our point of contact, where friction is occurring, the displacement at that point is 0. So if you think of work being force times displacement, our displacement at the point of contact is 0. So friction doesn't actually do any work. Okay? Really, all that friction is going to do is it's going to convert what would ordinarily be kinetic energy, it's going to convert that into rotational kinetic energy. Okay? But we don't actually lose any of our total energy. Okay? I'm glad I remembered that. I had not written that in my notes. All right, so our total energy at the top is equal to the total energy at the bottom. That means that our GPE at the top is equal to our KE plus our RKE at the bottom. So GPE at the top, that's mgh. KE at the bottom is 1/2 mv squared. Remember, rotational kinetic energy, as long as you're going through smooth rolling, is just beta times your kinetic energy. So I notice that my masses cancel. All right. Remember, we had decided up above that H is delta x sine theta. So I'm going to make that substitution here. So we've got G times delta x sine theta equals, so I've got 1/2 v squared times beta times 1/2 v squared. So this is 1 plus beta times 1/2 v squared, right? Okay. And we had one other relationship, which is this. Remember, v squared is that, right? Just from regular old kinematics. So let's do that substitution. So now I've got G delta x sine theta equals 1 plus beta times 1/2, and then v squared was 2 times the acceleration of my center of mass times delta x, right? So let's see. The 1/2 and the 2 cancel. The delta x and the delta x cancel. So if I divide both sides by 1 plus beta, I get the acceleration of my center of mass is g sine theta over 1 plus beta. All right, so there you go. That's the acceleration of an object rolling down a hill. Smooth rolling down a hill. Okay, so assuming there's no sliding, it's rolling down a hill. The acceleration just depends on the angle and the rotational inertia of the thing that's rolling. And notice, if it was just sliding, then the acceleration is just g sine theta, right? So your acceleration is slightly less as your rotational inertia gets bigger, which makes sense, right? Okay. Okay, so that is one way of doing it. The big thing that I should probably point out here, again, this is really not a super efficient way of finding acceleration. What this would be better for is, you know, finding the velocity at the bottom, okay? But I like it because it illustrates this idea here, okay? All right, so let's see if we can do this another way that's maybe a little bit more practical, okay? So here's our next option. All right, so this is the way that I usually would see this in a textbook, okay? So here's our inclined plane with our object, which is rolling down the ramp, okay? So you're gonna have your FG perpendicular and your FG parallel. You're gonna have, oh, another quick thing I should comment on, and this is super important. From this point forward, because we're now dealing with torque, when you make your free body diagrams, it is important that you draw the force emitting from the object at the point at which the force is applied. In other words, gravity is applied at the center of mass. Normal force is applied at the point of contact, okay? Friction is applied at the point of contact. That's an S for static, okay? All right, so the next two methods I'm going to use to calculate the acceleration of this thing are as follows. We're going to basically do net force equals net force and net torque equals net torque. The difference is where we choose our pivot point to be, okay? So the first time I'm going to choose my pivot point to be the center. So I'm going to do net force equals net force, and net torque around the center of mass is equal to the net torque around the center of mass. All right, so we're going to solve it based on that, okay? So, so notice when we do this, first of all, our FG perpendicular and our normal force cancel, right? So let's do net force equals net force. So net force equals net force gives us this equation. You're going to have FG parallel pulling down the hill minus friction is working against you. It's static friction, right? Preventing the object from sliding. That's got to equal mass times acceleration. All right, so let's do a couple substitutions. FG parallel is just mg sine theta minus our force of friction static is equal to mass times acceleration. Okay? So let's solve this for the force of static friction. Is that how I'm going to do it? I think it is. So force of friction static, if you add and then subtract, gives you this. Yeah, I don't know. This is going to be kind of algebra-y. Okay, so we're going to do m times g sine theta minus a. I don't know, maybe that might not be the best way to do this, but okay. So there's one of our equations. Okay? Now notice we've got two unknowns. We don't know friction, and we don't know our acceleration. Okay, m, g, and theta would all be given to you, right? Okay, so now next step is to look at our net torque equation. Okay, so let's scroll down a bit. So net torque about our center of mass is equal to the net torque about our center of mass. So if we do that, if our pivot point is here, then gravity doesn't provide a torque because the lever arm is 0. Normal force also has a lever arm of 0 because it's just pointing right at the pivot point. So our only net torque is by friction. So the net torque about the center of mass is going to be the torque from friction. And that's got to equal I times alpha, right? Okay, so torque from friction, that's force of friction static times the radius. That's equal to I, which is beta mr squared, times alpha, which is just A over R. Okay, so what do we notice? Well, let's see. If we multiply both sides by R, you can see that all of the R's cancel, right? Because you're going to get R squared over here. Those are going to cancel those. All right. So, oh yeah, I wish I'd done this a little bit different. But whatever, it's algebra. Okay, so now we've got force of friction static equals beta ma. Oh, that's actually a really useful result. Right? When you're rolling, your force of static friction is just beta times ma. Okay, cool. So now what I'm going to do is I'm going to combine these two equations here to give me this. Beta ma equals mg sine theta minus a. Let's see what happens here. So the m's are going to cancel. So let's move all of our a's to one side. So I've got beta a plus a equals g sine theta. This is the same as a times 1 plus beta g sine theta. Oops, equals, sorry. And then divide, and you get a equals g sine theta over 1 plus beta, which is the same thing we got before. Cool. And I just realized I was really sloppy. All of these a's should be acceleration of the center of mass. Okay? All right, so that's another way of doing this. What you should take from this, the big trick here, notice I did all of this with no numbers, which I know can be a little bit intimidating. But you can solve problems like this with numbers. The big takeaway is this. Two unknowns, two equations. Those are your two equations. Net force equals net force, net torque equals net torque. Okay? All right, so here's the third option. This one is sweet. It's super quick. All right? And for whatever reason, this is another one of those things. I don't know why they don't do this more. One of these days, I'm going to run the world, and I'm going to be like, here's how you do physics. Because I almost never see people solve rotational problems using this little trick, okay? It does happen. It does happen. I'm being a little bit, I don't know, egotistical, I guess, right? I'm going to get over myself. All right. All right. So here we go. So here's the third option, which I know it says option 2, right? I'm like, look how great I am. I can't even count to 3. Okay. So here's the other idea. So I'm going to do the same idea as I did before. Net force equals net force, net torque equals net torque. But this time I'm going to choose this as my pivot point, the point of contact. All right. This picture probably doesn't show up very well, so if you guys remind me to show you in class what this is, you know what, just remind me to talk about this in class, okay? Remind me. The picture in video 12.1, and I'll show you this. It's kind of a neat picture. All right, so anyway, I'm going to choose this as my pivot point, okay? So, oof, this video is going to be a long one, isn't it? What are we at here? Holy moly. 30 minutes already. Yikes. All right, well, here we go. Muscle through. Oh no, dropped my pen. All right, so here we go. Inclined plane. Rolling thing. I, about the center of mass of our thing, is still beta mr squared. Okay? So, but what I'm going to do this time is, instead of doing my net torque around the center of mass, I'm going to do my net torque about my pivot point. Sorry, about my contact point. Okay? So what does that mean? Well, let's see. That means that friction's not going to provide a torque. Normal force isn't going to provide a torque. FG perpendicular doesn't provide a torque. Only FG parallel does. Right? So here's the deal. One equation. Net torque about point P is equal to net torque about point P. All right? But before we can do anything, the problem is, this is the rotational inertia about the center of mass. We need to know the rotational inertia about point P. So you've got to use the parallel axis theorem, which is no big deal though, because check it out. Rotational inertia about point P is the rotational inertia about the center of mass plus mh squared. Remember that? Parallel axis theorem? Parallel axis theorem. Here, h is the distance that you moved your pivot point, and we moved it from the center to the edge. So here, h is just r, right? So this is beta mr squared plus mr squared. Holy beans. I just said holy beans. That's 1 plus beta times mr squared, right? So that's the rotational inertia about the contact point. Okay? So now we're going to go over here. So let's see, net torque about the pivot point. Well, the only thing that's providing torque is FG parallel. It is a distance of r away from my pivot point, and that's got to equal I about our pivot point times alpha. Okay? So here we go. FG parallel, that's just mg sine theta times r equals I about our pivot point is 1 plus beta mr squared, and alpha, that's just a over r. Look at that. One fell swoop. We're done. Look at this. M's cancel. Multiply both sides by r. You've got r squared on both sides. Divide both sides by 1 plus beta, and you get a equals g sine theta over 1 plus beta. I again was sloppy. This is about the center of mass. All right. So these three solutions are arranged, I believe, in most frequently. This one's the easiest, using the center mass is next easiest, and then the energy one I really would use for finding velocity or height at a point. Okay? Cool. So let's see if we can apply all of this nonsense to an actual problem. All right? If you need to pause the video here, I know this is a long one. Pause it. Go get yourself a glass of water. In fact, I'm going to pause it and have a sip of my delicious coffee. Ooh, that was close. I almost deleted. And my coffee was not, in fact, delicious. It's actually very cold. Okay. All right, so let's do an example here. Do you know what? This yo-yo example's, it's almost the exact same thing we just did. I think I'm going to skip the yo-yo example. There's a problem similar to this on the homework, and I really think it's going to be one of those things where Try it on your own. So here's the deal with the yo-yo, all right? Let me say this. So you've got your yo-yo. So there's a couple problems like this. So you've got, imagine a yo-yo, right? So here's the outer shell of your yo-yo. Here's the hub that the string winds around, right? So there's two radii here, right? And so what forces are there? Well, the string winds around the hub, so you're going to have a tension force up here, right? And then gravity pulls down on the thing, right? So if you call this your pivot point, then you can just do the torque provided by gravity is equal to I about your pivot point, use your parallel axis theorem, times alpha. Okay, that's kind of the deal there, all right? And there's a problem on the homework that is similar, where you've got, it's this like, it's a wheel, and you've got like a hub sticking out of it, and then it rolls down a ramp like this, so that this is all sort of underneath the ramp. Okay, so again, exact same idea. Choose this as your pivot point, and your FG parallel provides your torque. So the torque provided by gravity parallel is equal to I about this pivot point times your alpha. Okay. So, all right. So I do want to do a numeric example though, and this next one is a good one. I forgot about this. Here, read this. Come up with an answer. We'll vote at the beginning of class if you guys remind me. I'm totally going to forget, but if you remind me, we should talk about this. This is a question, I've seen this on tests before, and I would say less than half of the students get it right the first time. So read this, think about it, okay? And we'll talk about this in class. All right, cool. Moving on. Rolling spool, another thing. I'm going to show you this in class. All right, remind me. There's a ton of stuff you guys got to remind me. One of these days I'll get my stuff together and I'll keep notes of like, here are the things I need to do. But I'm not there yet, so remind me. Whole bunch of stuff to show you. Ooh, it's exciting. All right, here we go. All right, here's the example that I had in mind. All right. Okay, so it says in the figure a constant horizontal force of 12 newtons is applied to a uniform solid cylinder. So I for our solid cylinder is 1/2 mr squared. You know, we know our mass and our radius. Let's just, do we want to find it? Yeah, I'll just leave it. Okay, let's see. The problem tells us that the cylinder has a mass of 10 kilograms and a radius of 0.10 meters. Okay? All right, and the cylinder rolls smoothly on the horizontal surface, right? So it wants to find the acceleration of the center of mass. All right, please watch this part. There is something really surprising, and when I solved this, when I wrote up my solution here for the notes, I stumbled onto a thing that I'd forgotten about since I wrote this example last year. There's something sort of weird here, okay? All right, so what is the acceleration? So you've got this rope up at the top that's pulling on it and trying to cause it to rotate, all right? And so A says, what's the acceleration of the center of mass of the cylinder, okay? So I'm going to solve it two ways because I want to make a point, okay? So the first thing I'm going to do is this. So what forces are on it? Well, there's this applied force pulling it forwards, right? There's gravity, but that's not going to provide any torque about either of these two pivot points, right? So I don't need to worry about gravity. And then there's friction, right? Okay? And so my knee-jerk reaction is the rope is pulling this thing forward, and so friction is going to prevent the thing from sliding, right? So you got to have some static friction there to prevent the object from sliding, right? And I will, I'm going to give away the punchline. It turns out my friction is currently in the wrong direction. All right, but I don't know that yet. I don't know that yet because I haven't solved the problem yet. Okay. In other words, well, I'm getting ahead of myself. Okay. All right, so let's solve this thing. All right. So A says, what is the acceleration of the mass of the cylinder? So I'm going to do exactly what I recommend. Let's call the contact point P, let's call that our pivot point. Okay. So let's calculate I about point P. So that should be I about the center of mass. Notice this is about the center of mass, right? plus mh squared. So let's see. So we've got 1/2 mr squared plus, my h is just r, right? So that's 3/2 mr squared. So that's the rotational inertia about that pivot point. Okay? So I'm going to just do a net torque about P equals net torque about P. Well, the only force that's providing a torque is this applied force being applied up here, right? So that's going to be 12 newtons is the force times my lever arm. That's double my radius. So 0.2 meters equals I about the pivot point, which is 3/2 times the mass times the radius. Don't forget to square it. Okay, right? Because this r was dependent on the shape of the object, and the radius of the object is 0.1 meters. Okay, so here's I times alpha, where alpha is just a over r. So a over 0.1. Okay, so chug through the algebra on this, solve it, simplify everything. You end up getting 2.4 equals 1.5a. And so the acceleration turns out to be 1.6 radians per, nope, sorry, meters per second squared. Okay, so that's that. All right. So let's go back and do this again, using the other pivot point. Okay? And something really weird happens. Okay? All right, so here we go. So let me, I'm going to clear some of this. You know what? Here, let's do this. Okay, so I'm going to do it again. But this time I'm going to choose the center of the wheel as the center of mass. Okay? So I'm going to do a net torque equals net torque about the center of mass. And I'm going to do a net force equals net force. Okay? So watch what happens. So if I do net torque equals net torque, then about my center of mass, oops, let's see, so net torque about the center. So that's going to be, that's the torque provided by our applied force plus the torque provided by friction. That's got to equal I times alpha. Notice I now is about the center of mass. So about my center of mass, let's see, my torque from my applied force is 12 newtons times 0.5 meters, right? No, 0.1 meters. Right? Because that's how far, if this is my pivot point, then my radius is just 0.1. Okay, plus my force of friction times 0.1. Notice my assumption is that both forces are producing clockwise torque, right? So these are both positive. Okay, I'm assuming that that force of friction is producing a positive torque. So right now I'm assuming that the value of my frictional force is a positive value. That's my assumption. Okay? Equals I, which is 1/2 the mass. Notice it's 1/2 now, right? Because it's about the center of mass. Okay, so times our mass times our radius squared times alpha, which is a over r. Okay, so if you simplify this mess, you get where is my paper? Okay, so if you simplify this mess, you end up getting, well, so I canceled all of the 0.1s. And so you get 12 plus the force of friction equals 1/2 MA 10 times A. Okay? I'm going to leave it like that for a minute. Okay, so that's that. Now, if you do a net force equals net force equation, then you're going to get Well, let's see. My net force is the force of friction. No, it isn't. Well, it is, but I want to write it different. It's the applied force minus my force of friction static. Again, I'm assuming that the force of friction is positive, so I'm putting a minus in here to take away a positive value, right? Because I'm assuming that friction is working against my positive 12 newtons, okay? Okay, this is important. This was where the weirdness is, all right? So this equals mass times acceleration, so that equals 10 times A, right? Okay, so, oh, I guess I could have put my 12 in here, right? Okay. So if you double this top equation, if you double this, then it gives you 10A, right, over here. So my other equation now is 24 plus 2FFS equals 10A. Okay, and so now I can set these things equal to each other. All right, so what I get is 12 minus FFS equals 24 plus 2FFS. Add the FFS, subtract the 24, you get negative 12 equals 3FFS, and my force of static friction comes out to be negative. All right? So if I blindly go along and just solve this, I'm going to go over here where I've got a little bit more room. So if I go, all right, cool, so now I just go net force is mass times acceleration. So my net force, this actually, I guess, yeah. So basically what I've just stumbled on is, remember, we went through this whole problem assuming that our force of friction was positive, and we just solved it and got a negative value. So that means that I was wrong about the direction that I had my friction. So my friction must point to the right. That's very strange. All right. So if we assume that, then what that means is, now I've got this drawing. I've got 12 newtons here from my applied force, 4 newtons here from friction. So acceleration is net force over mass. My net force is now 16 newtons divided by 10 kilograms, and it gives you the same acceleration we got before. The big question is, why the bleep is friction pushing this thing forward? Well, here's why. What that's telling us is if this force is big enough, so you've got this wheel, right? So imagine this. You've got this wheel sitting on a ground or hoop or disc or whatever it is, and you're going to pull it forwards with this force, right? Isn't it possible that you could pull it so fast that it would just spin in place? Right? But what's happening here is friction is preventing that from happening by pushing forwards. Okay? In other words, that force of friction is preventing the wheel from spinning in place. Okay? Or spinning but still moving forwards. Okay? So, long story short, there's a lot going on here, and I know this is a really long video, but you really need to have a full understanding of these rolling problems, because they do come up a lot, okay? And the tools that I've used here to solve these problems, they come up a lot on the AP test, all right? Especially on the FRQs, which is where the bulk of the points are, okay? All right, so then once you've done this, B and C are easy. We've already done part C. We found the force of friction. It's got to be 4 newtons to the right. Angular acceleration, that's just A over R, so whatever that is. 1.6 over 0.1, so 16 radians per second squared. All right, cool. I am way, way over my limit. Let's get out of here. Holy moly.